All right. Yeah, so I'll talk about Python and gamma ray astronomy. I'm Christoph Deil from the MPI for Nuclear Physics in Heidelberg. And at the beginning, I have an introduction to just gamma ray astronomy and the space and ground-based telescopes that we have, because I know that most of you aren't gamma ray astronomers and may not be familiar with the field and with the data we have. So for this first part, I'll go very briefly over the slides. And there's no time to cover astrophysics. So if you're interested in gamma ray astrophysics, there's a good recent review paper you can go to. So just to say, well, gamma rays are the high energy end of the electromagnetic spectrum. We observe photons ranging in energy from MeV to 100 TeV energies. And just for comparison, optical light is at 1 eV and X-rays are keV photons. And because gamma rays are absorbed by the atmosphere, the way to observe them is with a space telescope, and the best space telescope there is at the moment for gamma rays is the Fermilab space telescope. It's a pair production telescope. So what happens is that a photon comes into a tracker, converts into an electron-positron pair, and then you reconstruct these tracks and get the event direction out from the incoming photon. There's also a calorimeter at the end, which gives you the energy of the photon, and there's an anti-coincidence shield where you can distinguish charged particles from photons. So this is needed to separate out the very small fraction of gamma rays actually hitting the telescope from the much larger fraction of cosmic rays. So basically, the high-level data you get out of a gamma ray telescope is an event list table with the time, energy, and position of each photon. And then you have a spacecraft file telling you when the telescope pointed where, and instrument response functions like effective area and point spread function, which you can then use to do science analysis for gamma ray data. And this is just an overview of how the Fermilab observations work. Well, the mission started in 2008. It's been continuously serving the sky for the past 7 years. It's got a very large field of view, so you observe a good fraction of the whole sky at any given time. And then it orbits the Earth and has a rocking pattern. And this means that you observe every source every few hours, and you get an exposure pattern which looks something like that. This is the result. Fermi has given us the first good view of the gamma ray sky ever. The energy range is about 100 MeV to 1 TeV. And the angular resolution is, like, at low energies 10 degrees, the point spread function, and at high energies, very good, 0.1 degree. So what you see is galactic diffuse emission, and then they've detected 3,000 point sources in the sky, extragalactic and galactic. And every source is a powerful cosmic particle accelerator. So Fermilab is an awesome gamma ray telescope, but at roughly 1 TeV, it runs out of statistics because gamma ray spectra are steeply falling power laws. So the brightest sources you can observe, like the Crab Nebula, even if you observe them for 10 years with a telescope with a detection area of 1 square meter, you just get a few photons and you cannot do astrophysics with that. So for very high energy gamma ray astronomy above 1 TeV, you need other telescopes. And this is where the Cherenkov telescope arrays on the ground come in. The way this works is that you have a gamma ray photon hitting the atmosphere. This creates an electron-positron shower in the air, which emits Cherenkov light, which is optical light, and then you image this shower from the ground. And if you build many telescopes and use the shower images, you can again say what kind of particle it was. Was it a photon or a cosmic ray? And you can reconstruct the event energy and direction. So, and by making the atmosphere part of the detector, you can get a square kilometer detection area for gamma rays, and you can do TV astronomy. So these are IACTs, Imaging Atmospheric Cherenkov Telescopes, and the currently existing instruments are MAGIC in La Palma, Veritas in Arizona, and HESS in Namibia. They cover roughly the energy range of 100 GeV to 100 TeV, and they do pointed observations at a given point in the sky with a field of view of a few degrees. So each of these arrays has a few telescopes and a total cost of the order of $10 million. It's been built by collaborations of like roughly 100 astronomers, and the data and software from these IACTs is not publicly available. It's built and maintained by these collaborations. Compared to the Fermilab, this is a NASA mission. with a much larger budget, and there all the data and software is publicly available. So just to show you some result in TeV gamma ray astronomy, so the first source was detected pretty recently in 1989, and by now we already have 150 sources detected. It's a very young branch of astronomy, and we've surveyed the galactic plane. So the next step is now to build the Cherenkov telescope array, CTA, build more and much better Cherenkov telescopes. So this is a project where 100 telescopes in Chile will be built and 20 on La Palma. It's not quite final, site negotiations are still ongoing. It's an international consortium already consisting of 30 countries and 1,000 astronomers being members of the consortium. The cost is on the order of $300 million, and it's a real change in the field. So this will be an open observatory with guest observers and an archive, as is common at other wavelengths. So the status is that prototype telescopes are taking data. Array construction will start in a year, and then hopefully the full array will be operational by 2024. Now, is this a big or a small data project? I would say both. So the raw data consists of images or little movies of these air showers I've been talking about before, and the raw data rate is pretty large, like 10 gigabytes per second. So at the low level, it's a big data project. And then in the data center, you have a low-level CTA pipeline, which does calibration, event reconstruction, gamma hadron separation, and so on. And the result is a much smaller data set, where, again, just for the gamma ray events, you basically get a few numbers for each event, and astronomers can then download this as FITS data on the laptop and use it for normal science. And this part of this software is called the CTA science tools. So you have the pipeline and the science tools. Now, coming to codes and Python and gamma ray astronomy. Traditionally, for the past decades, gamma ray astronomy has been mostly done by people from high energy physics. And this meant this huge C++ package called root. It provides everything, like it's a scientific computing library. It does I/O for C++ objects automatically. And there is a Python interface, PyRoot, but it's not much used because root comes with an interactive C++ prompt and interface called, it was aclick and now it's Cling based on the Clang compiler. And that's why Python hasn't taken off. It's more popular now, but it's mostly, it doesn't play a big role. So the status for these telescopes is that ground-based gamma ray telescopes have proprietary software, C++ root, no Python, and also the data formats are proprietary. Whereas for space-based mission like Fermilab, at the low level it's the same, but then at the high level you have data in FITS format and science tools, which are C++ with a Swig Python wrapper. So now, what will happen for the CTA software? Very active development is going on, both for low level and high level. There's many ideas and prototypes floating around. I would say that making decisions and going towards production codes has been hard for the past few years because there's no strong central management. It's not an ESO project that's centrally managed. It looks like most CTA software will be C, C++, or Python. So at the low level, there's also Java used. And somewhat surprisingly, no one is proposing to base it on root. And I think it's kind of, maybe it has to do with this change that now we have sources, and it's changing a little bit from being a community of high energy physicists that now build particle detectors that do astronomy to being really part of the astro community. So kind of one of the major questions has been, like, how do you construct the CTA software? Do you start with C, C++ libraries and then have Python scripting on top? Or do you just implement it in Python, and where efficiency is a concern, extend Python with C, C++? And it's interesting to see which way it's going, because it looks like the low-level software, where you have big data, is the prototype for this is Python. It's a CTA pipe package. It's on GitHub. It uses the AstroPy package template, and it's built on the scientific Python stack in AstroPy. And this was chosen over many C and C++-based proposals and prototypes pretty recently. It's still a bit controversial if Python is efficient enough for this part of the software. And just personally, it's pretty nice to have a package which is Python 3 only, where you can do less testing and compatibility stuff. For me, it's the first package I can work on, which is Python 3 only. Then at the high level, at the science tools level, there's at least two approaches being proposed. One is to have a huge C++ library called gammarays, which is a generic library for gamma ray event data. And then you have instrument-specific modules for CTA, Fermilab, and so on. It has no dependencies except cfits.io for easy maintenance. So it doesn't even use things like WCS lib or ERFA. And that's why it has over 100,000 lines of code already. And then for the CTA, you have the C tools, which are F tools like command line utilities for IACS analysis. And it is being proposed as the official CTA science tools. What we've been working on is a different approach called GammaPy, a Python package for gamma ray astronomy. It basically has the same goal, where you take gamma ray data and produce high-level results like images, spectra, and light curves. It's a provisionally accepted AstroPy affiliated package. Fermi analysis, we want to try to implement it both ways, both by re-implementing the analysis directly and by connecting to the Fermi science tools via FermiPy. And as you can see here, the development has been pretty active over the past 2 years. So we use this approach where we have Python first and use dependencies, so it builds on AstroPy and Sherpa, as well as NIMA, FermiPy, and a few other packages like reproject and FootUtils. And it's, in this sense, similar to the approach from CTA Pipe, but different from the GammaLab C-Tools approach. So the status is that so far we've mainly used this within HES, which is the experiment I'm part of, where we export data to FITS and then implement high-level analysis with GammaPy. We're thinking about proposing it as a prototype for CTA science tools, but the short-term plan is we want to do a 1.0 release this summer and then a paper soon after. So the development is, I think, pretty standard. Like we use all of the awesome and free tools and infrastructure, just like AstroPy and most other open source Python packages these days. Development is on GitHub. Testing is done on Travis CI. We use PyTest and Sphinx, and a lot of our users and developers use Anaconda to install the software. So just to mention some of the other packages we build on. One is Sherpa, which is an awesome general modeling and fitting package. It's similar but different from AstroPy modeling. And this is actually something we've been struggling with, making a decision which modeling fitting package to use. There's NIMA, which is an AstroPy affiliated package for non-thermal SED modeling, doing the fitting via MC or Sherpa. And there's FermiPy, which is a Fermilab data analysis for humans, you could say. So it's a much nicer interface where you have a config file and a high-level class to do the analysis compared to using the Fermi science tools directly. Just one application example, what you can do is with very little Python code, you can start with an event list where you just have the energy and position for each event, make a counts map, make a background model, and then by comparing those, make a significance image and run a peak finder like from FootUtils or something and get out a source catalog. I think this is very powerful, the combination of packages, AstroPy, and the ecosystem has built. So just to wrap up, my summary would be that space and ground-based gamma ray observations are used to study cosmic particle accelerators and the non-thermal universe. At the moment, we're in the state where for ground-based gamma ray astronomy, it's done with C++ root-based code in private collaborations. But now CTA is coming, which will be an open observatory with open data and open source software. And there's competing concepts on how to implement the software and what dependency stack to use. And there's a few packages where people are using the scientific Python stack and AstroPy to implement stuff. So just to finish, I'd like to thank a few people for organizing this conference and for the opportunity to give this presentation, but also for building the AstroPy package and community as a whole. And specifically, like the technical things that we are using for gamma pi and other development, and that are very valuable to us, is to have something like AstroPi Core, to have the package template, the continuous integration helpers, or the conda packages via the AstroPi channel. So thank you.
Questions?
So you mentioned about gammarays, so that's not the package, but I was curious about the comment about, so it doesn't use sort of more WCS lib, but then, does that really make it easier for long-term maintenance to not, because if you have 120,000 lines of code, it's harder to maintain than 20,000 lines. So is it, can you expand on that argument?
And same thing for the earthless stuff. There's a lot of time goes in to make that correct.
Right. Yeah. I guess I'm just curious. Like, was it the maintenance reason that led them to not use the?
Yes. Well, it's not been accepted, but the person developing it, like his reason is really like the long-term maintenance, and he'd ideally like to have GammaLib also be adapted for future gamma ray missions. So it's a generic library that can run for many decades. So even CTA, the timescale is the software has to be maintained for 20 years. And if you build your software on NumPy and SciPy and AstroPy, is it going to be maintained and stable for the next 20 years? And how much effort do you have to spend over the next 20 years to adapt your software as your dependencies change? So I think it's a valid argument to say that maintenance costs are important and are lower if you don't have dependencies. But of course, having lots of lines of code also means maintenance. So it's a subjective thing. I'm not aware of studies that show either way is right or something like that.
The other Tom?
I guess that's pretty similar to my question, which was just trying to understand the political process or the organizational process that's choosing between these two different methods of supporting science analysis, and when will there be a decision which is made, or is it sort of being put out there as an open competition, or are people just kind of going and hoping to produce something that clearly wins, or will there be a hybrid approach in the end?
So the process is not quite clear to me, and also the timescale when a decision will be made is not clear to me. So for the LOLA, the software, there actually was a call for prototypes within the last year or two, and so on. And at the end of looking at all these prototypes, so there were 6 or 7 prototypes that were C++ based. The guy responsible for this work package, he basically said, I don't like any of them. And he proposed this Python stack approach and convinced, I don't even know what the board within CTA is that makes these decisions to go this way for now. And for the science tool software, this decision hasn't happened yet. And we'll just have to see what happens within the next year or two. But the timescale for the whole experiment is really that things have to happen now. Where is the timescale for CTA? I guess it's further up here, because array construction will start in a year, and then we'll have first science data within the next 2 or 3 years. So things have to happen now soon.
So if you end up with a tool that you're able to develop more quickly and is adequate, then that may be a way to win the battle, essentially, by just showing up to the finish line first with something that works really well. But I guess it depends on resources and how fast and efficient the competition are with their own tool set. We see people that do C++ have lots of libraries that they're
Yeah. Well, it's not a centrally managed process where you have one institute or one management deciding how to build the software. You have different groups throughout Europe or the world that are proposing stuff, and then I'm not involved in the CTA decision processes, and I don't really know how it's going to play out. Yeah.
It's possible that both may be supported, perhaps.
Well, this is hard to imagine, that officially the CTA decides to maintain both for the next 20 years.
Well, you can say for a while and see which people end up using it.
For a while, Shaw supported SLang and Python both, and for a number of years. Both languages were supported, and we had to do everything in duplicate. It was a big mess.
One more question.
I wanted to revisit the point you made a moment ago that you're not aware of any studies that compare maintainability of your own code versus dependencies. Maybe this is a question, an open question for everybody. This is probably something that has been addressed in industries. Are there any studies that actually test, like, that have looked at whether or not code is maintainable with or without dependencies, or is this something we should really be trying to figure out if somebody has done these studies? Because it's probably an important thing when selling, well, when looking for funding, selling to funding agencies, telling them that you're cheap, why, whether you're cheaper. We can find these, whether this is hopefully corporations trying to do this. They try to understand what's cheaper. They don't want to lease the data they have.
So just to say, I'm very interested also to about this LSST, AstroPy people talking at the end. So I want to join for this next weekend and just listen in and see how they build their C++ Python interface and what libraries they choose to build their software on. I'm very interested to see this.